Okay, our next talk, Anubhav will tell us about ERA, encoded P2 codes, and how to use them to get fast SNARKs.
Cool, thank you. Hi, my name is Anubhav. I'm a PhD student at the University of Pennsylvania. And yeah, this is going to be maybe, I guess, like the second core talk of the day. And it's maybe going to be like a little bit similar to Andre's talk, but maybe also a little bit different. Instead of, I guess, sketch codes, I'm going to be talking about like these things called error codes. Great. So first of all, what are SNARKs? SNARKs are succinct non-interactive arguments of knowledge that allow a prover to prove statements to a verifier with a short proof. I'm not going to dwell too much on that. I'm sure all of you are familiar with them. And hash-based SNARKs are secure SNARKs in the random oracle model, which require like no additional assumptions. And they enjoy many, many nice features, such that they're plausibly post-quantum secure, they have no public key cryptography, they have fast provers, and they have transparent setups. And these are all nice, but there is one not-so-great feature that they have, which is that they have quite large proofs. So for example, if you look at the opening size of polynomial commitment scheme, for bullet proofs, which are not hash-based, you can get proof sizes that are like in the range of about 5 to 10 kilobytes. But if you look at the potentially like the state of the art in terms of proof size for hash-based SNARKs, you have stir and whir, which are in the range of 200 to 400 kilobytes. So there's a huge gap here. Great. There is another additional property that some hash-based SNARKs do exhibit and some hash-based SNARKs don't exhibit, which is field agnosticism, which is the property that provers can compute proofs over an arbitrary field of large size. And in particular, this means that the field doesn't need to be F50 friendly, doesn't need to have mean to be binary extension field, doesn't need to have like any particular structure. Great. So there are some hash-based SNARKs. Okay, so first of all, why do we care about field agnosticity? The main problem that we want to solve is non-native field arithmetic simulation. So for example, if you have a computation defined over a field FP, what's that? Oh, cool, thank you. So for example, a prime field like SECP256K1, and say you have one gate in your computation, which is just like a simple addition gate, which is taking in two integers, two values A and B, and outputting their sum modulo P. Okay? And so, say now you have a SNARK prover that's defined under FQ, where Q is not equal to P. So now you can imagine this is like an F50-friendly field. And what will happen is that in order to be able to simulate this one single gate of the computation over FP, you will have to convert it to a computation over FQ, and then you will, of course, like have this like a blow up in your circuit size. So in order to just simulate one operation that looks like A plus B modulo P, you would end up with like a bunch of gates that are modulo Q. Great. One of the applications of field-agnostic SNARKs shows up in ECDSA verification. So we want to verify a large batch of ECDSA signatures, which is a computation that's defined over this particular curve. And there are numerous applications of this particular process, including ZK rollups, ZK bridges, anonymous credentials, you name it. Great. If we use something like Fry, Stir, or Whir, then we would need to convert the computation to be over an F50-friendly field. And this can lead to like a pretty big circuit size blow-up, like close to like 25x. And therefore, you would also have a prover time that blows up by 25x as well. Great. But the good news is that there already does exist like pretty good work on field-agnostic SNARKs, like breakdown and baseful. So why do we care about this? So out of like the many nice features that some SNARKs have, you might now, there are some, okay, sorry. The SNARKs that are not field agnostic, like Stir and Whir, have proof sizes that are in the range of 200 to 400 kilobytes. But if we want to talk about SNARKs that are field agnostic, like baseful and breakdown, then they actually have a bigger problem, which is that they have very large proofs. And these proof sizes can range from like 10 to 20 megabytes for baseful and breaking base, and 20 to 50 megabytes for breakdown and EA code-based SNARKs. And these numbers are for like fairly large instance sizes. So the question naturally is that can we get better proof sizes for field-agnostic hash-based SNARKs? Amazing. Before we get to answering that question, we should go over some basic background about SNARKs, which I'm sure all of you are familiar with, but just for the sake of completeness, we'll go over it once. So SNARKs have a standard recipe from PIOPs and PCSs. You first have a polynomial interactive oracle proof for a relation R, where the prover is allowed to send polynomial oracles to the verifier. And a polynomial oracle for a multilinear polynomial in particular looks something like where the verifier can ask for the evaluation of this multilinear polynomial at any point, and then the prover is able to convince the verifier that, hey, this polynomial does evaluate to that value at this particular point. Great. And how do we instantiate these polynomial oracles? We do that via polynomial commitment schemes. So you have a prover and a verifier. The prover first commits to the multilinear polynomial M. Then the verifier sends back this evaluation point. And then they engage in an interaction where the prover proves to the verifier that the polynomial does evaluate to Y on Z. And the proof size of a SNARK is approximately equal to the proof size of the PCS, and the PIOP contributes very little to the proof size. And therefore, in order to get better proof sizes for SNARKs, we need to get better proof sizes for PCSs. Okay. The hash-based PCSs have kind of a standard recipe from codes and IOPPs that we're also going to go over. So we have a multilinear polynomial M hat, and we want two ingredients. We want an error-correcting code with some encoding function, and we want an interactive oracle proof of proximity for the code. So we have a prover and a verifier. The prover first sends to the verifier this commitment, which is just the encoding of the polynomial under this error-correcting code. And what the prover really sends to the verifier is an oracle to this encoding. And then the prover and the verifier engage in an interactive protocol where the prover proves to the verifier that this W is indeed close to the error-correcting code C. And this is the interactive oracle proof of proximity. And during this interactive protocol, of course, the prover also sends more oracles. OK. And finally, after making some queries to the oracles, the verifier outputs accept or reject. Now, this whole scheme gives you an IOP for a polynomial evaluation claim. And once you instantiate the oracles via Merkle commitments, and then you apply fiat Shamir, you finally get a hash-based PCS. All good. OK, so the two key metrics of a PCS that everyone cares about are prover time and proof size. The proof size in most hash-based PCSs in some ways kind of dictates the verifier time as well. So we can think of the proof size as being like a reasonably good proxy for the verifier time. So for the prover time, the two factors that contribute to the prover time are the encoding time of the error-correcting code and the prover time of the IOPP. For the proof size, you have the relative distance of the code and the communication of the IOPP that are the two key contributing factors to the proof size. And so therefore, if we want fast provers and small proof sizes, what we need from the error-correcting code is fast encoding and large relative distance. And what we need from the IOPP is fast prover and low communication. OK. And now we've shared all the background, we can finally, I guess, talk about our actual results. So we introduced a new family of codes called encode, repeat, accumulate codes, which are linear time encodable codes inspired from repeat, accumulate codes, which you might have seen in the recent work of Blaze. These are parameterized with a base code B, a repetition parameter R, two permutations, and a multiplication vector V. I will shortly get to what these individual things are and like what the encoding procedure looks like. And but what you should think of like this error-correcting code that serves as an input to our overall error-correcting code as just some code that has very fast encoding, but not maybe super great distance. So you can think of it as being, like for example, you could even use like Bolt, or you could use Lightning, which is the concurrent work with Bolt, or you could use Breakdown. And the reason we say that is because the results that we obtain show that the base code distance that you actually use for obtaining error codes doesn't need to be very large. It can be extremely small. But after you apply like all the operations that we apply to obtain our final error code, you can get distances that are like quite large. And in particular, if you have the freedom to be able to like really boost up your repetition parameter, then you can end up with the distances that are like quite high. OK. Because of the strong distance guarantees of our code, we can already plug in our code into like old IOPPs, in particular the IOPP of Ligero and Breakdown, which uses interleaved codes, to immediately get better proof sizes than like previously discussed IPPs like breakdown. So for example, this is like a small experiment with like a relatively short message length. But if you use a error code with repetition factor 4, then you can see that we get commit times and evaluation times and verifier times that are all very similar to breakdown. But our proof sizes are like smaller because, and the proof sizes are mostly smaller because of like our increased distance compared to breakdown. Breakdown, here we parameterize to have distance 0.1, but our error codes with rate 4, with r equals 4 have distance 0.228, so therefore they're able to get smaller proof sizes. Okay. One thing I want to very briefly mention is that conjecture error codes are the same as error codes, but we omit like a 1-1 multiplication step in the middle, and we can talk about it after the presentation if people are interested, because this is something that I'm quite curious about if this is possible to do, because if we are able to remove that step, then we'll have better encoding time, and then our codes will also be defined over rings, which is quite interesting. Okay. So we additionally also develop a new IOPP for error codes. And the new IOPP has these asymptotics, linear prover time, lambda log n query complexity, and small communication overhead, which then leads to a PCS with these parameters. And you might say that, OK, asymptotics don't really tell you the whole story. Like, it's really the concrete proof sizes that matters, because I promised to you that basefold and breakdown and all of these hash-based PCSs have these concrete proof sizes in megabytes and stuff. So what about concrete numbers? And we also have some concrete results for a new IOPP. So first of all, state-of-the-art field-agnostic PCS for proof sizes is at least basefold and breaking base. And we compared ourselves to an optimized version of basefold. So it kind of turned out that when we actually started comparing ourselves to basefold, we found out that you can actually take a basefold implementation and optimize it quite a lot for its proof size already, because through like kind of new techniques that have been, I guess, discovered in the last couple of years since basefold came out. And but even if you apply those optimizations to basefold, we're still able to get approximately a 60% reduction in proof sizes for large instance sizes for comparable prover times. And in particular, you can see that like our proof sizes are at most 4 megabytes for message length 2 to the 32. And I want to say that the work is, of course, still not done, because as I mentioned to you before, non-field-agnostic SNARKs like STIR have 400 kilobyte proof sizes. And so there is still like quite a big gap from what we achieve and what STIR can get. And I will say that I believe that even though like we are able to get better proof sizes than basefold, there is still a good amount of work to be done on the IOPP front for our paper. And I think Giacomo and I both believe that we can do much, much, much better than what we already have. OK. So the remainder of this talk is now going to be like maybe quite different. I'm not necessarily going to talk about IOPs and SNARKs and things like that anymore. And I'm really exclusively going to talk about how do you actually analyze the distance of error codes. But you might say that, OK, Anubhav, you haven't even told me what the encoding procedure for error codes looks like right now. How can I do the distance analysis of them? And what I hope to be able to do through the remainder of the talk is, through the distance analysis, I want to be able to motivate what the encoding procedure should look like. Great. So the starting point of our codes are going to be binary array codes, which are parameterized as 2 permutations and a repetition parameter r. And I'm going to have like a running example running on the side to demonstrate what's going on. So you have a message that's of length k. And the first thing you do is you repeat every element of w r many times to get that. And here r equals 2. Then you permute the resulting vector under this permutation to obtain like a new vector. After the permutation, you apply a prefix sum, which is what we call an accumulation operation, and to, in some ways, boost the Hamming weight of the vector that you have. So earlier, you can see there were only 2 ones in your vector, but now, because of applying this prefix sum operation, you are now getting a little bit extra ones. And then you permute it again, and then you apply a prefix sum operation again. And the resulting, and this entire code is called the binary RAA code, and this is going to be our starting point. And so the first question that we ask is, how do you actually compute the relative distance of RAA codes? And first of all, the relative distance of linear codes is the minimum relative Hamming weight of a code word. So we really don't have to worry about anything other than trying to see if we can boost up the number of non-zero entries in our code words. And there are only really two steps that boost the relative Hamming weight of our encoding, which are the accumulate steps. So these are the two steps 3 and 5 over here. And so therefore, these are the steps that you really just need to study in order to be able to analyze the distance of error codes. And how do you analyze the accumulate steps is what we will get to now. And our focus is just going to be for this talk, going to be just on the first accumulation operation, because the second accumulation operation is a bit tedious to handle. OK, so how do you analyze the first accumulate step? You consider first one fixed vector W, and you split it up into weight of W plus 1 intervals. So what do I mean by that? So if, say, this is your input word to your accumulate step, then you divide it up into these intervals, which are designated by the non-zero entries of W. So the 0th interval ends just before the first non-zero entry. And the first interval starts at the first non-zero entry, goes up to the second non-zero entry, and so on. And now, when you apply the accumulation operation to this, you get a vector that looks like this. And you can see that the 0th interval now is off. Like it has zeros. The second interval is on, and the third interval is off. And you can imagine that in a binary case, this is kind of what's going to happen. You're going to have off, on intervals. And therefore, exactly half the intervals are going to be on, and exactly half of the intervals are going to be off. Exactly up to plus minus 1. So now, using the fact that W is uniformly random among the set of vectors with weight W, because we just applied the permute step just before we apply the accumulate step, we can show that the sum of the lengths of the on intervals is large. And this, in some ways, showing this is the main challenge for the binary case. And we're not going to dwell too much on this, because move on. And with this, you can argue that AW has large weight. OK. But the problem is that this is just one message, right? I said that, like, OK, we're considering one fixed vector W. And we're showing that, like, the output of applying the accumulate step to this W has large weight. In order to be able to actually show that your error correcting code has large distance, you need to be able to do this for all messages, right? Because the distance of a code is the minimum Hamming weight across all possible messages. OK, so how do you do that? First of all, the question that you need to ask is, how many messages do you actually have, right? And only messages of weight W over R could have produced a vector of weight W after repetition. And there are only N over R choose weight W over R ways to choose such vectors. Because these are just the non-zero entries that you would pick from N over R many indices. And once you know how many messages that you have, all you have to do is apply a union bound over them. OK? Once you have applied that union bound, you need to then finally apply union bound over all choices of the weight, and you're done. But the second union bound is somewhat insignificant because there are only n choices. And the real big number that you actually have to contend with is this, like, n over r choose weight W over r. So that's great. But what about large Q? So far, we have really been only discussing the binary case. So one of the not so great things about the binary case is the first sentence over there. That half the intervals are on and half the intervals are off, which restricts your distance, relative distance, to be at most 0.5. Just because of this property, and in general for, like, binary codes as well, you cannot have relative distances that are more than 0.5. But for larger Q, you can hope that this is not true, right? Because just as I was mentioning, in the binary case, you have this 0-1 flipping phenomena, that after an on interval, you always have an off interval, and after an off interval, you always have an on interval. But in the non-binary case, you don't have this. An on interval can be followed by another on interval. But the new problem is that now we have to apply a union bound over way more many vectors. So previously, all we had to do for choosing how many possible inputs you have is choose the indices and nothing else, right? But now, in addition to choosing the indices, you also have to choose what non-zero entry you're going to have in those non-zero indices. Okay? This is a problem because Q can be potentially very large, and you can't just use the randomness of the permutation to be able to get a probability that's small enough to overcome this large union bound. So how do you handle this large union bound? And it's broadly a two-step analysis. We proved that, first of all, we proved that lots of intervals are on. We'll see what lots here means. And then we proved that the total length of the on intervals is large. And we have to apply this large union bound over both of these steps. And both of these steps require two different solutions. Like, there's no one single thing that actually helps you apply a union bound over both of these things. So the solution to the first problem is that we introduce a multiplication step. And in order to be able to union bound over all of these many things, we're going to use the randomness of this multiplication vector. And then for the second step, we actually don't even end up doing a union bound over all input messages, but rather something that or rather all input configurations. And we're going to see what configurations mean later. OK, so proving lots of on intervals. And how much time do you have?
7 minutes.
OK. OK, so how do you handle the large union bound for proving lots of on intervals? We introduce a multiplication step, and we use the randomness of the multiplication vector. So what do I mean? We sample V uniformly random from the field. And I'll, again, have a running example on the side. And I'm going to demonstrate what the encoding now looks like. So now, instead of a binary vector, you have a field vector. And the entire encoding procedure looks exactly the same, except after the permutation, you also do this element-wise multiplication by V. And doing this multiplication by V now actually helps you prove like something very interesting, which is that you can now prove that almost 1 minus 1 over r fraction of the intervals are on. So you no longer should do just half the intervals being on. You can now show that as r grows, the fraction of the intervals that are on also grows. And that is partly why when we saw the distances earlier in the table, we were able to get like larger and larger distances for larger and larger r. OK, so let's see be a constant that's like between 1 and 2. And we're going to the specific statement that we're going to prove is that 1 minus c over r fraction of intervals are on. W is an input to your accumulate step. And for each of the intervals, like we defined earlier, we define an indicated random variable, which is 1 if the ith interval is off, and 0 if the ith interval is on. I know it's kind of flipped, but bear with me. It's by design. And we assume that all the xi's are mutually independent. And this is, categorically speaking, not true. But you can assume that they're independent for now, because you can handle the non-independence with just some extra care. OK. So now, this is what your input vector to your accumulate step looks like. You have 3 intervals. And the important thing to notice here is that if you want interval 2 to be an off interval, there really is only one value in the entire field that actually makes that interval off. Every single other value will keep the second interval on. And here, for example, that value is q minus 5. And the nice thing that we now have is that each non-zero wi is uniformly random. And why is that? Because we applied the multiplication step. So when we multiplied with this multiplication vector, we ensured that every single non-zero entry was a uniformly random field element. And therefore, we're able to get that the probability that any of the xi's is 1 over q minus 1. It's very, very small. OK? And finally, we want to show an upper bound on how many off intervals you can have. You want to show that the probability that you have more than CL over R off intervals is very, very small. And how do you do that? You apply a Chernoff bound. You have your expectation, which is L over Q minus 1, where L is defined as the weight of the vector. And if you just go through the steps, you can see that you will be able to get this expression, which, very importantly, is inverse exponential in Q. And because it is inverse exponential in Q, we can actually now do a union bound over all the many inputs that we described earlier. So we no longer have that problem that, oh, we have these exponentially many inputs, we can't union bound over them. But now we do have like this extremely inverse exponential probability of failure. Therefore, we are able to union bound over them. OK, so union bound over. I'm just going to walk over the union bound argument very quickly, which is that we have the failure from one message, looks like that. The number of messages look like that. You just multiply them together to apply the union bound, and you get that the probability of failure for any message is their product. This remaining stuff that is not a function of Q is completely insignificant if Q becomes large enough. And therefore, if you set, because C was greater than or equal to 1, the failure probability is inverse exponential in Q. So you can see that the exponent of Q minus 1 is L times 1 minus C divided by R, and C is greater than 1. So that is the exponent is negative over there. And because this happens, if Q is sufficiently large, then all messages have 1 minus C over R fraction of on intervals after the first accumulate step. And the one small problem that is left to be solved is that the exponent of Q is this value, L times 1 minus C over R. So if C gets like very, very close to 1, as we usually set it to be, then it's not necessary that this exponent is very large, and therefore it's not necessary that this whole probability is very small, right? And this is finally where the final, I guess, change of our algorithm comes in, which is that we need the input weight L to be somewhat large in the first place. And how do we make that input weight somewhat large? We preface the encoding process with a very basic error correcting code. And so this is what you do. You just take what our previous encoding procedure was, and then you just prepend this like encoding procedure under B to get this WB. And now this is also why the distance of this base code B can be very small. Like in the table that we saw, we were using values that were like 0.001. And the reason it's like that small is because this weight or this distance shows up in the exponent of the field size. So you don't actually need it to be very large for the probability to actually become very small. And this is what our final encoding procedure for error codes looks like. You have M, you encode under a base code, you repeat, you apply permutation, you apply multiplication, you accumulate, you apply permutation, you apply multiplication, and you accumulate. And that's the entire encoding procedure. OK. How much time do we have? 1 minute. OK, great. I'm going to very, very, very briefly go over the second step, which is proving that the on intervals are long. And the rough idea is that you don't actually need to union bound over all the exponentially many different inputs, because you can club a lot of inputs together. And the reason for that is that if you have a weight, if you have a vector W, you can consider its configuration, which is just the same vector, but you replace all the non-zero entries with ones, and you replace the zero entries with 0. And we have already proven that a large fraction of the intervals of W are on with high probability. And now, if we somehow also prove that so now this statement is a little bit messy, so it'll take a second, that the probability that there exists any set of more than 1 minus C over R times L intervals that have small length is small. This entire argument can be shown with a counting argument, and we will not dwell on this. But if you are able to show this, then you are able to show a similar statement about W prime as well, where W prime is any vector that has the same configuration. So if the first statement is true for a W with a particular configuration, then the second statement is also true for any W with the same configuration. And therefore, this is the rough idea as to why you don't actually even have to union bound over that many inputs, and you are able to just union bound over these many configurations instead, which is not a function of Q at all. And finally, in order to obtain your final distance, you apply union bound again. You just solve for the largest delta such that that particular expression is true. And that you can do with a simple binary search. That is your final output distance. And that is a very, very slight lie, because at the beginning of the talk, we said that we're only going to analyze the first accumulate step. So indeed, this is our distance that we obtain after the first accumulate step. What you get after the second accumulate step is, again, a little bit more complicated and tedious. And what I'm going to do is I'm not actually going to give you a mathematical proof of it. I'm going to give you a proof by intimidation. Yeah, OK. This is the last slide. OK. This is what the actual algorithm for the final thing looks like. It's like has a Hessian in it. It has partial derivatives in it. It's a whole mess. But the nice thing about this is that it's very easy for a computer to implement. You can just, we have a Python script for it that you can check out, where you can just plug in your desired lambda, desired r, desired base distance, desired block length, desired field size. You can put in these 5 values. You'll just get your distance as your output. OK. But even though this does look complicated, I do want to say that it is conceptually very simple, and it is just very messy analysis and combinatorics that you don't have to contend with. And that is all I have to talk for today. Thank you so much. That's the paper. That's the distance analysis. And yeah, thank you for very much.
A quick question while the next speaker sits up.
So I'm kind of curious, how should I be thinking of this distance amplification technique as compared to traditional kind of ABNNR and AEL distance amplification at a high level?
Yeah, I think the main difference is that those techniques are explicit, right? They are deterministic. And this is a completely randomized technique.
No, so think of using a random expander there.
Oh, so I don't know if you can, I guess, necessarily look at applying a permutation and an accumulation operation as similar to applying an expander graph.
Your thing takes an arbitrary code and amplifies its distance,
yes.
Right?
Yes.
That is a similar thing to what those
yes.
classical transformations do.
Yeah, but the technique is quite different, I guess.
Sure, but if tomorrow I have a code and I want to amplify its distance, which technique should I use?
Oh, in terms of practical numbers, if you really care about the numbers.
Yeah, how does it compare, in whatever way?
I think the one thing that we did compare to was AEL. Mm-hmm. And the main problem, I think, that we ran into with AEL was that there was a very, very large alphabet size blow-up. And I think when we tried to compute the exact numbers for it, if you wanted to get even a distance of 0.5, when you're amplifying from a distance of say 0.01, this blow-up in your alphabet size was on the order of millions. Mm-hmm. And therefore, it does not seem like something that you can. It seemed very hard to make practical.
So there's an issue with concrete numbers.
Yes, concrete numbers.
But in terms of asymptotics or general behavior,
with asymptotics, I'm not sure exactly what the gap is. Yeah.
So I have a question. So you showed that you did repeat, and then you permuted, and you multiplied by this V, right? But so whatever you analyze for that, you always can take a code word that is just, you divide by V, and essentially, isn't it the same code?
What do you mean? You divide by V?
So you multiply by V, right?
Yeah.
OK, so if you take some code word and encode it, then you multiply that state by V. Now take the same code word, divide it by V, right? And you should just cancel that effect. So overall, can't you just get rid of this multiplication? Maybe I missed something with...
So I'm not sure why that would work exactly. So you're saying that you encode, then you multiply, and then after you have multiplied, then you divide again?
Take two code words that they're the same, except one is a division of the other by V.
One is the division of the other by V.
OK, let's take it
offline.
Oh, I
see, you're describing a bijection, I see. But yeah, let's take it offline. Yeah.